Well, it occurred to me it's taking me an awfully long time to answer my question, why Lie algebras? And we are still in chapter 0. I'm still trying to get to that punchline, but we're just about there. So we've talked about algebraic groups and their Lie algebras, and we've set this whole story up nicely. So at the end last time, I was talking about this group homomorphism int, which sends a group element G to the automorphism of the group G given by conjugation. And I talked about the group homomorphism add, which goes from G to automorphisms of its Lie algebra. Now this time, unlike automorphisms of the algebraic group, automorphisms of the Lie algebra is itself an algebraic group because it's a closed subgroup of the general linear group on that underlying vector space, little g. So this add here, this is called the adjoint representation. Of the group G. And so if you remember add G for a group element little g, add G by definition was the differential of int G. And I think we also proved that for G being the general linear group, the way add G in the general linear group acted on a matrix X in the general linear Lie algebra was just the obvious thing, just conjugation by that invertible matrix. So we'd done that. And then finally I had this little a add, which was this big add. This is a morphism of algebraic groups. So you can differentiate it. Its differential gives you a Lie algebra homomorphism from the Lie algebra G to the Lie algebra G, which is a subalgebra of the general linear Lie algebra. So little a add is the differential of that morphism of algebraic groups. Big A add. And I think I noted that it sent an X in the Lie algebra to the derivation of the Lie algebra G, sending an element Y to just taking the commutator, taking the Lie bracket with X. So those were things we were talking about last time. I thought I would just start out today by doing one example, and I'm kind of going to do the easiest example, but it's still interesting and it'll kind of tie up a few loose ends. So in this example, the group G is going to be the group SL2 of K. So it's Lie algebra, got this German G, that's the Lie algebra little SL2 of K. This is three-dimensional because it's 2 by 2 trace 0 matrices. So for this, we've got this adjoint representation of the group SL2. So this is a homomorphism, a morphism of algebraic groups from SL2 of K to the general linear group of the vector space little SL2 of K. Since this is a three-dimensional vector space, we'll pick a basis in a minute. This is going to be the general linear group GL3. So there's this morphism of algebraic groups. So that's the adjoint representation of the special linear group. And the image. So maybe I should write down the kernel first. So it's rather easy to see what the kernel of this map add is in this example. It's just the scalar matrices plus or minus the 2 by 2 identity matrix, which in this case is exactly the center of the group G. And the image of add, being as this is a morphism of algebraic groups, its image is automatically a closed subgroup of that general linear group. So that's GL3 of K. And the image is what is the correct definition of the group PSL2 of K, the projective special linear group. So this is a closed subgroup. of GL of G. So I think I talked about PSL2 of K before, and I wasn't in a position to give you the correct definition of PSL2K. This is the correct definition. It's the image of the group SL2 of K under its adjoint representation. And so let me see, I think we did talk about some of these things a little bit before, but if the characteristic P of the field K is not 2, I think I noted before that PSL2 of K was actually isomorphic to SL2 of K, quotiented out by the center. That was just plus or minus the 2 by 2 identity matrix. And this was the quotient as an algebraic group, one of those things I hadn't actually defined. So this was as algebraic groups. But when P equals 2, something weird was going on here, right? You already see something strange going on, because in that case, this center of the group SL2 of K is just trivial. So when characteristic is 2, the center is just trivial. So that's a sign that something weird is going on. And in this case, PSL2 of K, defined in the right way now as the image of this adjoint representation, it's certainly isomorphic to SL2 of K as abstract groups, because the kernel of this map is just trivial in that case, but not as algebraic groups. So I thought I would try and think a little bit more about what's going on in P equals 2 here. So just thinking about this example. So in this case, you can think about little a add, right? So that's the differential of the big A add. So it goes from the Lie algebra of G, which is little SL2 of K, to the Lie algebra of PSL2 of K, which is little PSL2 of K, right? So by definition, or by our convention, that in little letters, that means the Lie algebra of the group in capital letters. And it's rather easy to see what the kernel of add is. It's just 0 when P is not 2. So actually add in that case is an isomorphism. But it is one-dimensional. In fact, it's all the scalar matrices, the 2 by 2 scalar matrices, when P equals 2. You see what's going on is that in characteristic 2, that has trace 0, that matrix, right? So the scalar matrices actually live in the Lie algebra SL2 of trace 0 matrices when P is 2. So when P equals 2, add is not an isomorphism, and that kind of explains why this add is not an isomorphism of varieties. Little a add is the differential of big A add. If big A add were an isomorphism, well, certainly its differential would be an isomorphism too, but it's not. So here's my kind of silly picture of the situation. Here's the Lie algebra little SL2 of K, this three-dimensional Lie algebra. In characteristic 2, the center of the Lie algebra SL2, it's these scalar matrices which do have trace 0 in characteristic 2. Z is one-dimensional. And here's my picture of the Lie algebra PSL2 of K. It's also three-dimensional. But what's going on is that this Lie algebra homomorphism, little a add, is killing the center, because the kernel of little a add is this center. So this little a add, it kind of sends this three-dimensional SL2. The image is just a two-dimensional subalgebra of the Lie algebra PSL2. And of course, it's not an isomorphism. In fact, for PSL2, the center, so always Z is center. So when you're doing groups, you use capital Z. When you're doing Lie algebras, you use these German letters for everything. So this German Z, that's the center of a Lie algebra. So in the Lie algebra PSL2, the center is 0 in fact always, but so maybe we should try and see that. I think it's so why is that? Okay, so I'm just sort of investigating this example, and so I want to just understand what is. So when P is not 2, SL2 of K and PSL2 of K, the Lie algebra of the group SL2 or the Lie algebra of the group PSL2, they're just isomorphic Lie algebras. In fact, they're both simple Lie algebras, but when P equals 2, these Lie algebras are not isomorphic. And the cheap way to see that is what I'm writing here about the center. The Lie algebra SL2 in characteristic 2 has a one-dimensional center, but the Lie algebra PSL2 has 0 center. So not only is little a add not an isomorphism, which is clear because it's got some kernel in characteristic 2. In fact, these Lie algebras are simply not isomorphic in any way in characteristic 2. So the only way to see that, establish this claim I've made about the center of the Lie algebra PSL2 is actually to calculate this Lie algebra explicitly. So let's kind of finish this example by doing that. So let's try and calculate PSL2 of K explicitly. So this is just kind of meant to kind of illustrate that these things are totally tractable things. You might not want to calculate them because I've got to work with matrices, but so we need to understand this adjoint representation from SL2 of K to the general linear group GL of the Lie algebra. So I'm going to pick a basis now. So I'm going to use the basis for the Lie algebra SL2. So that's 2 by 2 trace 0 matrices, and I'm going to use this basis E, H, and F. And so that's a basis for the Lie algebra SL2 of K. Okay, so this is so far this is in any characteristic. So what does this adjoint representation do? So let's take some invertible, in fact determinant 1, 2 by 2 matrix in the group SL2, and let's calculate what add of it does to our basis. So I'm trying to calculate what 3 by 3 matrix this is, right? So this big A add, it sends the group SL2 to the group GL3. So I want to know exactly what is this matrix. So to work that out, I've got to work out what does that do to each of the basis vectors for our three-dimensional vector space that we're using. So for example, if I wanted to calculate it on E, I would have to work out, so we're dealing with 2 by 2 matrices, so add is just conjugation. So I need to conjugate this E by that 2 by 2 matrix. So here's its inverse. And then you simply have to calculate that 2 by 2 matrix product. And with any luck, I did it right. It's not a very intelligent thing going on here. And I think you get that. And so this is calculating the image of our 2 by 2 matrix as a 3 by 3 matrix with respect to the basis E, H, F. Right, so the first column is what it does to E, which I've just calculated. So I've got to write that in terms of the basis E, H, and F. I think it's A squared lots of E minus AC lots of H and minus C squared lots of F. And then similarly, you've got to plug in not E, but plug in H, and then plug in F to calculate the second and the third columns of this matrix. And so I think I did it right, and I got negative 2AB, AD plus BC, and 2CD for the second column, and negative B squared BD, and D squared for the third column. Right, so these matrices for all A, B, C, and D in the field with AD minus BC equals 1 give exactly this group PSL2 of K sitting inside GL3 of K. So far I didn't use characteristic 2 at all. But now if we go to the case when P equals 2, then what have we actually got here? We've calculated, in characteristic 2, what have I actually got here? I've got A squared AC, there's no point writing minus, that's just 0. This is AD plus BC, which is AD minus BC, which is 1. That's just 0, B squared, BD, and D squared. And you see the equations that define this. PSL2 as a closed subgroup of GL3. The equations are, let me see, I need that, the 2, 1 entry, that's this AC. When you square it, it's the 1, 1 entry times the 3, 1 entry. And similarly, the 2, 3 entry squared is the 1, 3 times the 3, 3. And then T1, 2 is T3, 2 is 0. And T2, 2 is 1. And then finally, T1, 1, T3, 3 minus T1, 3, T3, 1. So that's this determinant of this 2 by 2 in the corner. Oh, well, we're in characteristic 2, right? So that's AD minus BC all squared by Freshman's Dream, which is 1. So, and I guess there's no real point writing minus because we're in characteristic 2. So those are the equations cutting out the group PSL2 of K as a closed subgroup of GL3. And once you've got those equations, now you can easily calculate the Lie algebra little PSL2 of K as a subspace of the Lie algebra GL3 of K. And so you get from those equations, you get that the Lie algebra PSL2 of K, it consists of all matrices of the form, I think I just, so this is now straightforward. It's matrices of this form for all alpha, beta, and gamma sitting inside GL3 of K. So hopefully you see that calculation is quite tractable. And then once you've got this Lie algebra explicitly, it's a 3-dimensional Lie algebra, you can then quite easily calculate its center to check indeed, as I said on the previous slide, that its center is 0, so that PSL2 is not isomorphic to SL2 as a Lie algebra. You can think about what the image of this little a adjoint representation is. I think the image of the little a ad, it's all these matrices where alpha is 0. So it's this 2-dimensional subalgebra in there. Okay, so enough calculating with matrices. It's kind of dumb, but it's a good example to sort of see what goes wrong when you're in positive characteristic. So for the remainder of, in fact, the entire course, I'm going to work in characteristic 0 only. In fact, since our field K is algebraically closed of characteristic 0, I'm actually going to just keep things really down to earth and assume that our field is just the complex numbers. So I want an algebraically closed field of characteristic 0, but we may as well just assume it's the complex numbers. So we're kind of leaving algebraic groups behind very soon. And for all of that discussion, I was working over an algebraically closed field, but it occurred to me that number theorists amongst you might have been a little disappointed by that. Algebraic groups are even more interesting over other fields, but to understand them over non-algebraically closed fields, the first step is always to pass to the algebraic closure of the field and understand them there. So I guess we're doing the right thing by assuming our field is algebraically closed. And now I'm assuming that it's of characteristic 0 as well. So the crucial thing about characteristic 0 is that it means all morphisms of varieties are what's called separable. And this has rather strong consequences for the relationship between algebraic groups and their Lie algebras. So I just wanted to try and wrap up this Why Lie algebras chapter by showing you some of these consequences which depend on the characteristic 0 assumption that's now in place. So I've done my best to avoid too much algebraic geometry, but this is the place where as soon as I have to discuss consequences of all morphisms being separable, that I can't avoid it any longer. But I'm not going to prove anything deep at this point using algebraic geometry. But I do need to just mention a few of these general things that we should really be doing if we were developing algebraic groups more seriously at this point. If G is an algebraic group and H is a closed subgroup, well, there's a way to make the set G over H of left cosets of H in G into a variety in its own right. In general, you can't do this without allowing more general varieties than simply affine varieties. It turns out that it's affine when H is actually a normal subgroup of G, but in general, it won't be affine. It'll be, in general, you need to go up to quasi-projective varieties to make this construction. I'm not telling you the construction. And then this has a universal property. It has the appropriate universal property. So this set G over H, if P is just the usual map sending a group element to its coset, that's actually a morphism of varieties. For this variety structure on the coset space that I'm not telling you about. In fact, that's an open morphism. And moreover, if you have any other variety and any other morphism F of varieties whose fibers are the cosets, the left cosets of H in G, then there exists a unique morphism F bar, making that diagram commute. So I'm assuming the fibers of F are exactly these cosets. So, of course, there's a unique set map F bar here, so that's a bijection. The universal property that I'm talking about says that bijection is actually a morphism of varieties, and it's an isomorphism if P is separable, an isomorphism of varieties. So if in characteristic 0, as all morphisms are separable, F bar is an isomorphism of varieties. So that's sort of the key difficult place in the development of this theory is getting to that universal, to that construction of the variety structure on the coset space and the proof of that universal property. So this has consequences. And let me just run through some of the consequences right away. So if you have a morphism of algebraic groups, then of course the kernel of that morphism is a closed normal subgroup of G. And if you look at that coset space in that case, I said that for normal subgroups, the variety structure on the coset space made it into an affine variety. It follows that this quotient is actually an algebraic group in its own right. If we let P be the quotient homomorphism, then and now we'd better assume that this phi is onto. If it's not, just replace H by the image of phi, which is a closed subgroup of H. Then now of course you know there's this group isomorphism phi bar induced. That's just the usual first isomorphism theorem for abstract groups. So this goes from it goes and am I going the wrong way? Yes, I probably am. I seem to have reversed my picture. So the universal property that I just wrote down, in this case, this phi bar, which is always an isomorphism of abstract groups, is an isomorphism of algebraic groups when the characteristic is 0 because everything is separable. Should mention one more thing about this construction of this coset space. The differential of P at the identity, so that goes from the tangent space to G at the identity, which is the Lie algebra, to the tangent space to G over H at the identity coset, and this has kernel exactly the Lie algebra of H, so that tangent space is actually isomorphic to the vector space G quotiented out by the vector subspace H. Okay, so this is consistent, this construction, that the tangent space of that variety G over H at the identity element is that quotient of vector spaces, the Lie algebra of G over the Lie algebra of H. So if I look in this picture and I look at the kernel of phi, so that's this closed normal subgroup in this case, the Lie algebra of the kernel of this morphism of algebraic groups, it's because of this diagram, commuting is exactly the same thing as the Lie algebra of the kernel of this quotient map P, and that's the same as the kernel of the differential of P here. And so the fact that this phi bar is an isomorphism of algebraic groups in this commuting diagram means that the Lie algebra of the kernel of phi is exactly the kernel of the differential of that phi. So that's the first important property. So this is a characteristic 0 only. We already saw a counterexample. In positive characteristic earlier today. If you just think about add from SL2 to PSL2 in characteristic 2, it's in this case the kernel of add is trivial, but the kernel of the differential was one-dimensional. So these couldn't possibly be equal in that case, just by dimension reasons. Okay, so characteristic 0 is totally essential for the Lie algebra of the kernel of a morphism of algebraic groups to be the kernel of the differential, that Lie algebra homomorphism. That's consequence 1. Consequence 2, suppose that H and K inside G are closed subgroups. Then the Lie algebra of their intersection is the Lie algebra of H intersected with the Lie algebra of K. This is all taking place inside the Lie algebra of our group G. Again, assuming we're in characteristic 0. Again, essential. And so how does this follow from what we've got? Let's look at the quotient G over K. So this is now just a closed subgroup. So this is this coset space. P is just that quotient map. So this is a morphism of varieties. And H sits inside G. And if I restrict P down to H, that gives me this morphism I'll call P bar, whose image is HK over K, which sits inside G over K. It's a closed subvariety of G over K. And then I'm also going to look at the quotient H over H intersect K, right? That's a closed subgroup of H, so I could look at that coset space. Let's maybe call that canonical map Q. So now because the fibers of this P bar, they're exactly the cosets of H intersect K, you get induced this unique Q bar, which is an isomorphism of varieties using characteristic 0, using separability here. So all this diagram commutes. So I've just proved the second isomorphism theorem, right? Except that I'm working in this the second isomorphism here is between these coset spaces with this given variety structure. Okay, so now we want to look at the kernel of the differential of P. That's just the Lie algebra of K. I told you that earlier. So the kernel of the restriction of P down to H, so the differential of P, the kernel of the differential of that restriction, that's just, I've just got to intersect the subspace L of H with the kernel of dP, which is L of K. So that's our right-hand side there. But because this diagram commutes, because this is an isomorphism of varieties here, I see that the kernel of the differential of that map is the same as the kernel of the differential of Q at the identity, and that is exactly the Lie algebra of H intersect K. So that's kind of how that goes. I'm just being a little hasty in going through these things because I'm just trying to get to my final punchline for chapter 0. So that's consequence number 2. Let's maybe just do one more consequence today. So here I want to talk about representations. So let this be a representation of our algebraic group G. So V here is a finite dimensional vector space, and this is a morphism of algebraic groups. Then you can take its differential, which goes from the Lie algebra of G to the Lie algebra of big GLV, which is little GLV. And this is then a Lie algebra homomorphism, so that's what's known as a representation of that Lie algebra. Let W inside V be any subspace. And so this third consequence I want to tell you about is about the normalizer of W in G. So that means the set of all elements of G which send W into W. The Lie algebra of that, so it's easy to see that this normalizer is a closed subgroup of G. The Lie algebra of that closed subgroup of G, it should be some subalgebra of the Lie algebra of G. What could it possibly be? Well, it's this Lie algebra normalizer. So this is all x in the Lie algebra such that, okay, maybe I was being a little, I'm going to write it and make sure I clarify what I'm writing, such that x of w lies in w. So this is a German n here. So when you're inside Lie algebras, for groups you use capital N for normalizer, capital C for centralizer, capital Z for center. For Lie algebras you use German N for normalizer, German C for centralizer, and German Z for the center of the Lie algebra. And I realized I shouldn't have written G of W here, I should have written rho of G of W here. And similarly here, I should have written d rho of x of w here. I mean, in this action here. So here's my third consequence. The Lie algebra of the normalizer is the normalizer in the Lie algebra. So again, this is kind of fairly easy to prove. So what you have to do is you have to use the quotient results that I've kind of muttered about earlier today to reduce to the case that actually this G is embedded inside GLV as a closed subgroup. Right? So you replace G by its image under rho. And now you look at the normalizer of W inside the whole general linear group GLV, and you think, what's the Lie algebra of that guy? Well, the claim is that that's the normalizer inside the Lie algebra GLV of W. So this is rather straightforward. What you do is you pick a basis for W and you extend it to a basis for G, and then you can see this normalizer sitting inside there as kind of block matrices. You end up getting kind of matrices of this form, where this is your basis for W. So that's the group normalizer, and it's very easy. And similarly, the normalizer in the Lie algebra has the same form, and so you see that the Lie algebra of the group normalizer is the Lie algebra normalizer in the case of the general linear group. That's kind of a triviality. But now the Lie algebra of the normalizer in the group G, well, that's just the group G intersected with the normalizer in the Lie algebra of W. So the normalizer in GLV of W. And now you can use property 2, which says the Lie algebra of an intersection is the intersection of the Lie algebras, which is the Lie algebra G intersected with the Lie algebra of the normalizer in GLV, which is the normalizer in GLV of W, and that is exactly the normalizer in G of W. Okay, so hopefully that made sense. So this is